Yeah, I have a meeting now for like an hour, 45 minutes, but then I can go downstairs. Is that okay? Some noise. Okay. Making here, is it okay? Yeah, I think it'll be okay. Okay. Thanks. Hello?
Hello? Yeah.
Hey, great to meet you, Phantom Man. I was just told by some people that are here doing some renovations on the house that there's going to be some noise.
Okay.
I didn't realize that before, but I apologize in advance. Hopefully it won't be too much of a blocker.
Oh, that's fine. It's not a real interview. So it's okay. Yeah. And you are practicing, so as long as you hear the problem and solve it. Okay.
Cool.
So, yeah, can you please briefly tell me about not about yourself, but like current situation and what you're hoping out of this mock interview?
Sure. Yeah, I have an interview coming up in like a week at Facebook for a developer evangelist job and on the Oculus team, and I haven't coded that much the last year or so, and I definitely haven't done like algorithm data structure stuff in a while. So I'm just trying to get my skills back and yeah, be ready.
Sounds good. Okay, so let's jump into problems, and we can solve like two to like 5 problems depending on the speed, and then based on that, I'll give you feedback, and I can give you feedback after each problem or towards the end, whichever works better for you.
Cool.
So which one works better?
I would say.
Yeah, let's do it like this. So for the first problem, I'll give you the feedback right after it, right? And then you, based on that feedback, you will basically accommodate that feedback if you want to in the next problems, so that yeah, we get some coverage there. And then if I see any overarching feedback, I'll give you that towards the end.
That sounds good.
Okay, cool. So should we start with like something medium or hard, easy?
Let's do an easy to medium one. Yeah.
Okay. So let's say we have like a stream of numbers like this, right? So each dot represents a stream, and at any given point t, we would get a API request saying get product of get the highest product of 3 numbers, right? Highest product of 3 numbers. So we are supposed to take the current status of the stream up to this point in time and return them answers, right? Answers. Yeah, I think that's pretty much it. And this stream is basically like ever growing, so it'll keep growing, and then suddenly someone will ask for another API request and so on.
Okay, great. So let's see. So basically, whenever this function is called, we look for the 3 numbers that are most recent in the stream and multiply them.
3 numbers which are highest, right? So we want the highest product of any 3 numbers in the stream. Yeah.
Oh, of any 3 numbers in the stream. Okay. Cool. So I'm going to do JavaScript just because that's what I'm most recently using and familiar with.
Yeah. No, but before you write anything, right? So what are you thinking? Like, how will you solve this?
Sure. So yeah, I'm thinking basically we're getting basically a stream or an array of numbers, and we're going to want to go through and find the 3 largest. So we would have maybe a hash table of like this. Let's see. Yeah, like a hash table with 3 keys representing like, the first, second, third highest numbers, and then the values, and then every time we have a number, we just check those three current highest values, and if it's higher than the third, we substitute out the third. If it's higher than the second, we substitute out the second, and if it's higher than the first, we substitute out the first.
But then you also have to update if let's say if the incoming number replaces the first, then you also have to evict out the 2 and 3 and replace 2 with 1 and 3 with 2.
Yes, good point. Yeah.
Okay. So that can be done with like 3 variables, right? So first highest, second highest, third highest. And what happens if there is like a requirement that instead of 3, it can be k, where k could be like 1,000, 10,000, whatever.
I see. Yeah. Well, I guess in that case, yeah, we wouldn't want 3 variables. We would want like a hash map
Mm-hmm.
or a hash table with all of the variables up to k.
I see.
And
But then what will be like the time complexity to figure out the highest product and to maintain the stream to track these numbers?
yeah, it would be k times n.
K times n. What is k and what is n? So k is the this k, and then what is n?
N would be the numbers in the stream.
Numbers in the stream. Okay. So for each number, you're saying you'll do O of k operation against your data structure, right? So you have a hash map, so you'll do a lookup in the hash map. You'll compare that number with all 1,000 numbers or 10, all the k numbers, right?
Yeah.
Okay. So can you like think of like improving that lookup or that O of nk to maybe reduce it to O of n log k or something?
Yeah, let's see.
Because the k can be large as well as n is also large and can be in like billion or something.
Well, I guess what we can do is get highest product of any, let's say 10 numbers. We can just keep yeah, it's interesting. I'm not sure how you would if there's a new number coming in and you're checking against the highest product of any, let's say 100 numbers or 5 numbers, like I'm having trouble thinking of how you wouldn't have to check that incoming number against those numbers to know if you should substitute it somewhere. Like,
Oh, you're saying like you're not able to come up with a way where you can't think of a way to like ignore comparing with every possible number in the k numbers.
maybe you can compare it just against the minimum and the maximum number, and then if it's
Mm-hmm.
if it's somewhere within that, you would
Mm-hmm.
just maybe then you would just boot the minimum number off the product. So
Okay.
just like basically just add the new number into the k number array,
Mm-hmm.
and
So in that case,
yeah
we'll have to maintain like sort of like a sorted array, right? Because if you just have like minimum and maximum, then that minimum and maximum can be disrupted as soon as like the new number comes in. You'll have to find a new minimum now and then put that to the front. Um, and to find a new minimum, you'll have to like go through all the numbers again.
that's a good point. Okay, so that's not optimal. Let's see.
So that in that approach, there is this angle where you keep the array always sorted, right? So you have like a sorted array of k numbers, right? So to maintain this array sorted, all you have to do is, for the new number, you have to insert it in the right position in this array. And to insert it, to find that position, it is log k time, right? Because it is sorted.
Yeah. But
So,
to keep it sorted would be a whole other thing, right?
Yeah, so you will find that position, but then once you find that position, you have to shift numbers around, right? That takes again like O of k time.
Yeah,
So
exactly.
yeah, there is like one data structure, yeah, which
Maybe
maintains a certain structure, which
like
easily gives you like the minimum or the maximum. Huh?
would it be a tree?
Sort of, yeah. Have you heard of like heap?
I've heard of it. Yeah, I don't know if I've ever I don't think I've ever implemented a heap.
No, but have you like used it, like priority queue heap?
I don't think so.
Okay, so yeah, this question is basically around that data structure. So heap is basically like you have like min heap, right, or max heap, and min heap will basically give you access to the minimum element in constant time. And to maintain this heap, it takes log k time, right? Like where k is the size of the heap. And it is sort of like a tree where you have like the topmost element, let's say like 1, and if it is a min heap, all the children of that node are going to be smaller than the node itself, smaller or at least equal. So this will be like -1, this will be -2, and -2's children will be smaller than -2, and so on. And you maintain this heap in this fashion, and then you do some operations on it whenever you insert new number and remove numbers, and all of those operations are log k. So yeah, so maybe you can look up into this data structure later. Or like I think like okay, so let me tell you one thing, right? You can still do it. I think if I tell you what the heap is supposed to do and operations on it, and maybe you can figure out how to solve this question. Is that okay, or should I switch the question?
No, that sounds good. Yeah.
Okay, so let's say like you have access to a heap, right? Like heap is equal to new heap, right? And you have operations which are let's say like peak, which will give you like the minimum element. So we are using min heap in this case. So let's say min heap. So heap.peak will give you access to the minimum element in constant time, and heap dot poll will basically evict out the element, and heap dot insert will add a new element into the heap. And both of these are log k. So this one is log k, log k, log k. So just using these three access pattern on the data structure, you should be able to solve it. So let's see if you can figure this out.
We would still need to be able to go iterate through every element to be able to multiply them all together, right?
Oh yeah. So but you can do that. I mean, let's say so let's say there is a heap dot get array or something. It gives you all the elements in the current heap.
Okay, cool. And then later I'll just have to look at how to actually implement a heap, but that's cool.
Yeah. I mean, in the interview, you don't have to like if somebody asks you this question, all you have to do is care about this data structure, not the implementation, unless they ask you to.
Oh, that's great. Okay. Okay, so
Also, just to reiterate, right? So never jump into like coding before you specify the approach, right? Otherwise, the interviewer is not clear what you're implementing. So make sure you communicate the approach which you are going to code before you actually code.
Okay. So I'm going to take in a string of numbers and then create a heap, and then create a heap with that stream. So let's just say you can pass in the numbers into the heap, and it organizes them based on what we want. I guess min heap. And then what I'm going to do is...
But we don't want to pass the whole stream into the heap, right? We only want to pass in new numbers and then maintain the size of the heap to k numbers. Otherwise, we won't be. If you are maintaining the whole thing in the heap, that is unnecessary, and then that also increases the lookup time to log n instead of log k.
So we'll just create a heap, and then what we'll iterate through all the numbers in the stream, and then we'll add if the current element that we're looking at is greater than the min element, we'll add it to the list of k numbers, and then we'll get the array and then multiply all the elements together. Or actually, no, we don't want to do that yet. We don't need to multiply yet. All we need to do is go through and go through the numbers one by one, and then get the minimum element. And if the element value is, if there aren't yet k elements, and we'll add the number, but once we hit k, then we'll check, and we'll only add it if the number is greater than the minimum value in the heap.
Number is greater than the minimum. Yeah, exactly. So you want to evict out like the smallest numbers and maintain the largest numbers.
Yeah.
Okay. So I have given you like this callback function, right? So whenever they tell you about like stream or something, basically you have like a callback or like a generator which gives you that new number, right? So you can have like something like next, which gives you that number, or this callback, something like this. So let's say you have access to this function. Each new number on the stream, you're receiving it on this callback. So you can listen to it and maintain your heap here. And then when somebody asks you for get highest product, you use that to return the highest product.
Okay, cool. So in that case, we'll define the heap outside of the callback, so it's still in scope. Then what we'll do, and we'll know, let's say, this is outside. So we already know what k is from outside of the callback.
Okay.
So what we'll do is say, if, is there a method on the heap for number of elements?
Number of elements. Oh, you mean like the size of the heap? Yeah. Okay, cool. Heap dot size or number of elements is fine. Yeah.
Size, or we'll say, if heap dot size is less than k, and we'll just add a number. Otherwise, we'll check and we'll say, if, I guess we can just do that here. If the number is greater than heap.peak, which is the minimum number, and what we'll want to do is, so heap.pull evicts out the minimum element?
Yes, yeah.
Okay,
peak gives you access to the minimum element without pulling it out. Yeah.
So what we want to do is get rid of that minimum element, because now we have another number that's bigger in the amount of k, and then we'll do heap.insert. And actually, we can make this cleaner by moving. Alt down doesn't work in this. Get rid of that, and really we can just say if number, if heap dot size is less than k and number bigger than heap. Oh wait, no. Let's see. I'm just gonna leave it the way it was. I think that was clear.
Yeah.
And no. Okay. And then once we go sorted array. So this is the callback number received, and then do we want to return the get highest product of any k numbers in here, or is that just the user will call that function at any time, and only if this heap we're keeping track of has k elements, then we return the product?
Mm-hmm. So you're maintaining that heap. Whenever the size is less, you're inserting it, and whenever the size is greater than the whenever the incoming number is greater than the topmost element, then you're removing, inserting. Okay, yeah, so looks good. And then there is that get product, right? So in the get product section, you just have to return your multiplied value. Yeah, which should be simple.
The user will call that separately, basically.
Yeah, that is called separately. Yep.
Okay, so basically, like, we have our heap. They call get product of whatever k numbers. We'll check again, and we'll say if we'll only even return the product if there's k elements. Otherwise, it's not a valid call, right? Okay, so if heap dot size is greater than or equal to, well, it should be equal to k. And what we'll do is we'll, let's say, convert the heap into okay. And then we'll go through every element. And we'll do product equals let's see, like 2 times 3 times 5. Yeah, product equals product times num. And after that, return num. Otherwise, if there aren't k elements yet and the user calls get product, we could just, I guess, return -1 or something.
Yeah, you can return like an error -1. Yeah, it's fine.
Okay. So let's say we have 2 equals 2, then the next thing is 3 times 2 is 6. Yeah, that should do it.
Awesome. And can you like improve the time complexity for the get product part where it goes from O of k to O of 1?
So we would just want to multiply all the numbers together at once. But we would still need to go through every number you still have to decompose that operation into a bunch of multiplications, right? Because you're multiplying all the numbers together.
So is there a way to like maintain that product as soon as you receive a new number instead of like calculating it after the fact?
Oh, I see. Yeah, we can do it. We can do it in our callback. One. Um, well, no, that wouldn't work because this is happening asynchronously, and if the user call, we don't know when the user is going to call get product. It could happen at any point, right?
Yes, any point. Yeah.
And so if it's happening at any point and we're getting our numbers from this API at any point, then at the moment that we get it, wouldn't we need to? No, I guess we can still keep the product up to date somehow in the callback. We would just have
exactly.
to. I guess we would just have to subtract. Um,
Multiply
we
and
would have.
divide, right?
Well, wouldn't we have to subtract our current, like the number that we're going to get rid of, the minimum number from the current product?
Yeah, so that won't be subtracted. It will be divide because we are multiplying it, so we'll have to divide it. If we are adding it, we'll subtract it, but in this case, we are multiplying things.
Okay. So then we would just do times equal. And then in here, just return product.
Okay. And what about like, okay, so for the initial one, you're saying if the heap size is k, otherwise -1. Okay, looks good. So what is like the overall time and space complexity for this?
Well, every time we get a number, well, I guess because number received is happening asynchronously, it's just happening at any point. So when we call get product, it's just O of 1 because we already have the product because we've just been keeping track of it over time. And in terms of the space, it would be K because the heap has to keep track of every single element up to K.
Okay, so it'll be so for each call of number received, the time complexity will be log of k, right?
Oh, every call of number received, yeah, log of K because that's the operation to insert. Yeah, I thought you were talking about the get product call.
Oh yeah, get product will be constant because you're already maintaining that product.
Yeah.
Okay, got it. And then overall for n numbers, how much will it be to maintain the heap?
It would be log of K, right?
For n numbers in the stream.
Oh, n log of K.
Okay, yeah. Okay. So yeah, so let's jump into feedback quickly and then we can move on to the next one. So here for this question, for any question, I guess, right? So make sure to ask about the input types, input range. So in this case, like you can ask questions like, will the stream contain 0? Will the stream contain negative numbers? And then there is one more thing which you have to be very aware of, right? Whenever you are multiplying large numbers, right? Or a lot of numbers, will the product go out of range, out of bounds of the data type, depending on the language, right? So for Python, it may not go out of range, but I don't know about JavaScript, but in Java, usually it goes out of range, right? So keep in mind of that thing. And then once you have asked about like the types and everything, make sure to ask clarifying questions around the question. So in this case, I think for stream, you were assuming that it is going to be an array or something, right? So make sure to, if you have any like implicit assumptions, make sure to bring them out so that if the assumptions don't match the interviewers, what the interviewer has in mind, they can correct you, right? So in this case, stream is like a generator sort of. So that's why we have this callback. So make sure to ask clarifying questions or clear out any assumptions, and then always specify your approach as clearly as possible to the interviewer before you jump into coding. And when you're specifying this approach, you can use like some sort of pseudocode or some English. You can write that down in the notepad if you want, or on the whiteboard. That is okay. And then once you have written down the solution, make sure to pick a simple example and walk through the code so that you can catch any obvious errors. This way you're also eyeballing the code as well, right? So you sort of like become a debugger, step through your code using a simple example, and this way you also help your interviewer understand your code as well. And then think about edge cases unit test after you're done coding, so you can think about like what kind of edge cases will you want to test. So for this case, you can test with like 0 with negative numbers if the interviewer tells you that they are possible, right? Otherwise you'll test this kind of solution with like if the stream size is less than k, or if the stream is really big and the stream has the highest numbers are really large numbers, which can go out of bound and cause overflow errors. So you can bring those up, and always like talk about time and space complexity. You can also like volunteer to talk about them. The interviewer does not necessarily have to ask you for it, and if you volunteer to give out that information, it just shows that you're confident and you know about these things, right? So yeah, these
You
were
were about the stream overflowing. Is that like you're saying I should just ask about like can the stream overflow kind of?
no. So it's not about stream overflowing. Stream will not overflow, right? So stream is just a generator which will just give you new numbers, but your product, the variable product, can overflow when you're multiplying numbers to it, right? Because let's say if you have like a number which is like 2 billion something, and then you have another number which is also 2 billion, then that will probably like overflow, and it'll give you a negative or like some answer which is probably not as expected, right? So make sure to bring those things. Yeah, basically shows that you're paying attention to detail. And yeah.
Cool.
Okay.
That makes sense. Thank you.
Yeah, no problem. So let's move on to the next question. Are you comfortable with trees?
No, but I want to get comfortable, so let's do it. Yeah.
Okay, sure. Or I can also give you like a recursion problem as well, which is based on.
Let's do tree.
Okay. This is yeah, and try to use the feedback which I gave from the previous problem, whichever you think you want to use in other interviews. Try to use in this one so that you get some practice on that. Okay, so this is a binary tree, right? And output we are looking for is like this: A, B, D, H, I, J, K, L, M, N, O, N, G, and C. Right, so this is the output. It basically starts at the root node, goes around the root node in anti-clockwise fashion, picking only those nodes which fall on the boundary, right? So anti-clockwise from root A, B, D, H. So all of these are on boundary and in anti-clockwise order: I, J, K, L, M, N, O, G, and C.
Okay. So you're basically saying like, given an input of a binary tree, return a flattened counterclockwise array of the numbers or the characters that are okay.
On the boundary.
Great.
Yeah.
On the boundary. Yeah. Okay. So we're taking in a tree, a binary tree, our input, and we will output an array. Okay, so what we'll want to do is start at the root node, and then continue to choose the right leaf in the relative direction if we were facing down, or like I guess facing up from the root. Yeah, like it's kind of weird, but down from the root. This is a leaf, but a real tree the leaves would be on top. So let's just say down from the root, continuing to move right to pick the minimum most value, or choosing the right node until we get to a leaf, and then once we get to a leaf, then we want to go back up to the parent, and then go to the left. Left being, I guess it would be left relative to the parent facing down, but really it's the right. From, if we're looking at it like kind of down, this was on a flat plane and we were above on the z-axis looking down at an xy plane. So we would go right, then we would go back up to the parent, and then we would ignore E because it's not in the boundary, and then go to the left. Interesting. Okay, so, what would be the best way to do this? So I guess once we go all the way down to the leaf, once we get to the first leaf, now we have to basically keep track, like maybe have a flag or something that say we've like hit the bottom rightmost or leftmost boundary. And so now all of the non-leaf nodes that we visit, we don't add to the array until we get to the rightmost node of the entire tree, and then the parent nodes of that one we start adding. It seems like maybe I'm making it trickier than it needs to be, but it seems like like you would need a lot of different like conditionals and flags and things like that.
But so I think like you're thinking about it in terms of like doing collecting all the nodes in one traversal, right?
Yeah.
So what if you could do like multiple traversals?
Interesting. Yeah. Okay. So maybe what we want to do is traverse all of the leftmost nodes till we get to a leaf, and then traverse all the rightmost nodes, and then just add all the leaves. So we would want to do we would want to do a different way of searching for each traversal. Like, does that make sense, or does that sound like it's on the right track?
Yeah, definitely. So how will you, let's say like you want to focus only on the left boundary, right? Where left boundary is A, B, D, H. How will you collect that?
Yeah, so we would just continue to, visit the left node of the current parent until we reached a leaf, until there was no next left node.
Okay. And what about like the bottom, like the leaf
The
nodes?
bottom. Yeah, for the leaf nodes, we would, I guess once we got to H, we would then know that we were at the bottom layer. So we would then we would go up to the parent, which is D, and then visit the right node, and then go up to the parent, which is B, and then visit E, and then visit the left and right.
So is this traversal like a continuation from the previous one, which was the left traversal, or is this a different traversal?
Yeah, you're right. I guess we could start over and then just, I was trying to should do a shortcut, but that probably makes it more complicated. So yeah, then we would start over at A, and then we would just go left, and then left again to D, and then right to I, and then start again at A. Well, no. And then we would just want to pop back up to B though, because otherwise you have to start back at A every time to get the leaves. Which
Oh yeah, yeah. So what I'm hinting at is like you can do one traversal and get all the leaves, just the leaves, right? So the way you can do it is like you can do whichever DFS you want, in order, post order, pre-order, right? It doesn't matter, as long as the left comes before the right, right? So as long as you do left traversal first before you do the right.
Yeah.
Do you follow?
Yeah. Yeah.
Okay. So what will that look like? So let's say we start at root A, and then what happens?
Then we go to the left to B,
Mm-hmm.
and then we go to the left to D,
Mm-hmm.
and then the left to H.
And then H is a leaf node, so you collect it, right?
Yeah.
Okay.
And then
you go back to D.
Then back to D. So then we would have to go right.
Yeah. Because you're
And
still
then
recursing on D. Yeah.
yeah, and then we go back up, and then we'd have to go to the right,
Mm-hmm.
and then go to the right, and then the left to get to J, and then back up, and then to the right.
Okay. So you know how to traverse the tree. Basically, you're doing in order, or not in order, but like pre-order traversal. And then you're collecting all the leaf nodes. So how do you know if it is a leaf node or not? When to collect this leaf node?
If the left and the right are null, it's a leaf node.
Okay, got it. So this way you'll be able to collect the left. And what about the right side? Is there any difference to the right side from the left side, or is it the same?
It's the same.
It's the same. I mean, on the left side you go left, on the right you'll go right, and but the order will change as well, right? So let's say you collected A, B, D, H for the left, and then H, I, J, K, L, M, N, O for the bottom, right? So this one is L, or left, bottom, and then you have right, which should be in reverse order, which is G and C. And you don't want to include A because it is already included in left. And here in the bottom side, you don't want to include H because you have already included it in left. And here you don't want to include. Here you're excluding O because ideally you'll have O as well, but you're excluding it because you have already included that in the bottom side, right?
Yeah, I'm realizing. I think would you be down? Because I know we only have like another few minutes or whatever. Would you be okay with coding it out and talking through it? I think for the amount of time we have left, that'll be more helpful than. I just don't think I'll be able to do this in the time we have, and I think it'll be helpful to watch you and hear you, and then I can use that to re-implement it on my own.
Okay, yeah, sure. So we have tree boundary, right? So this one can call get left boundary, right? Oh, what happened here? Okay, get left boundary, and then you'll pass the root, right? So the get left boundary will collect everything but the leaf node, let's say, because we want to ignore the leaf because we consider leaf as part of the bottom boundary, right? So we collect ABD from this side, and then we'll have get right boundary, yeah, get right boundary, and then we'll have this will collect all the bottom nodes, and then this will collect all the right nodes, right nodes, and get bottom, right? So we have these three things, and this will return you like a list. I'm just like sort of like pseudo coding it, but you'll get the idea. And then once we have this list, and even for left boundary, because we don't want to collect the root twice, right, on the left as well as the right. So what we can do is we can do root dot left, so that we ignore the root on the left and on the right, right? And then we collect the root here itself, where we say root dot value is equal to root. And in the end, because let's call this root value, or let's root dot value, let's put this in a list so that it's easy to add it later on. And then we return all of this appended, where we do root value plus left plus right plus bottom, right? And okay, so now let's do the individual pieces. So we'll do get left only, right? Yeah. So here, once we come here, what we'll do is first we'll check for existence of the root node. If it exists, then we'll do. If it doesn't exist, actually, then we can eliminate recursing further. So we just immediately, my keyboard sort of like double prints everything sometimes. So if there is no root, then we return, right, because the root is null, and that can happen when you're recursing on the leaf nodes, right? Otherwise, you know that there is a root, and in that case, you'll just collect that root. So you'll create a list here, list, empty list, and then list dot add append whatever root dot value, right? So you have added that particular node to your list, and you'll return that list. But before that, you also have to recurse. So there is an edge case on the left side. I don't know if you noticed, but let's say like if there is no left for a parent node, right? So what happens in this case? You'll go from A to B to E to I, right? So you'll go like in a zigzag fashion. So if there is a left node, you take that, which is your first priority. Always go left. But if there is no left, then the right node automatically becomes your boundary, right? So that's why we go from B to E and then E back to I, because there is a left node. We don't take J because there is a left node, which is I. So that is the edge case we want to take care of. So that's why, like, always think about edge cases. If you are not able to find the edge case, it's fine. The interviewer can give you that feedback or like hint, but always try to think about edge cases. So here, what we want to do is we want to check if the root has a. So before we even add anything to our list, we'll check if the root has a left. If the root has a left, then you do this part. You'll add this part regardless, yeah, because we are adding the current node. So this goes here anyways. And if the root has a left, you take left. You take recurse on the left side. Root dot left. Else you can blindly recurse on the right side. Root dot right. Basically, like, you're choosing which side to recurse on for this condition in this block, and then you're returning your list. So this takes care of the left side, and the right is going to be similar, except that the right will be doing this recursive part post recursion. That way you are recursing and then adding your current node. So that way you'll get the list in reverse order. You'll get, instead of C and G, you'll get G and C, right? Because we want it in a reverse order. If you look at the output here on line number 10, it is G and C and not C and G. Yeah. So if you do that for the right part, where you do a post order recursion sort of, then it reverses the order. So I will not go into the right side because it is very similar to this. And let's go into the bottom one. So
That boundary. The on line 23, when you're defining lists, if you're doing recursion, that list become empty every time? Like how is the list?
Oh yeah, yeah.
Too?
So what you can do is, because we are returning lists, right? So on each recursion, you want to make sure either you pass that list into the input function so that each recursion adds it to the same list, or whenever you are getting that list back, you can say returned list, right? Return list, and then you can do like a extend or something where
cool.
you return. Good catch. So you can do that. List is equal to this. Okay. And then we define the return list here. Return list, right? And then we do a list dot extend, and I think like extend probably returns the list too, so we just return that. And then we have the bottom side, so get bottom. So bottom is also similar, but a different kind of recursion. So here we just like recurse on the left or the right, and here we recurse on both sides, the left and the right. So you take the root node, and then same thing. We check for presence of root. If it is not present, then here we need to return an empty list. If it is not present, then you return an empty list. And if it is present, then what you do is you check is child or something. You can, that should be a simple function, right? So if the current root is a child, then you create a list and add that thing to it. Add root dot value. So if it is a child, you add it. Otherwise, you just recurse on the left and the right side.
Okay.
Root dot left, and here we do the same thing. Collect the return list. Get the okay. Yeah, return this one. And this two. And then you do list plus this one plus this, right? So here we are adding the current
root dot right, wouldn't it?
Oh yeah.
Okay, cool.
Basically, like you're recursing both the sides, collecting answers from both, and adding it to the final list with the initial list.
Cool. Okay, that's really helpful. So just to make sure I understand, for get right, basically do the same thing as the left, except instead of pre-order, we do post-order. So it would be if root dot right, and then return list equals get right boundary.
Okay.
Root dot right. Is that the only difference?
Yeah, I mean you can still do the same thing and reverse the whole thing in the end, or you can do it like recurse first and then collect the node. Yeah. So if it has a right node, you're going to the right side. If it doesn't, you're going to the left side, and then you're adding stuff to the overall, like the current node to the overall list here, right? So like this thing which we did here, just that. Yeah. So we add it, but before you add this stuff, you will basically do return list dot add root dot value, and then you return the return list. Do you follow? Because here we are adding all the nodes which come after the current node to the return list, right? So we get that answer, and then we are adding our current node after we have gotten the answer for all the nodes below that.
Yeah.
So this way we don't have to, I mean, you can still do it the same way as the left. Only thing is that you'll have to, when you get the answer, you'll have to do a reverse on the answer. But if you do it this way, which we currently did, we don't have to do anything.
Cool. Okay. Yeah. That makes sense. So that's called post order traversal.
I just made it up, but but it's basically like you're doing it post the recursive call. Instead of like collecting it before the recursive call, you're collecting it after the recursive call, because you're doing that recursive call that gives you all the answers, and then you're adding your current answer to that.
Yeah, that totally makes sense. Oh, wonderful. Okay, cool. I really appreciate that.
Yeah, no problem. We have 3 minutes. So let's see. So for this question, yeah, again, you forgot to ask clarifying questions, right? So make sure you ask clarifying questions about the input. Like what kind of tree is it? Is it binary tree? Is it binary search tree? Does it have any like special rules on the tree, or is it just like a simple binary tree without any rules? So in this case, it is simple binary tree. There are no rules, right? Like the tree can literally be just this, or it can be like A, B, where B is to the left, C is to the right, and then you'll have like, let's say like this, B to the right, and then B to the right. You can have duplicates, all of that. So make sure you ask all like the sanity check questions, where you ask about the type of input, range of input, the type of like the tree and stuff. And then once you have those, again the same thing, make sure you clarify your approach before coding. And talk about time space, think about edge cases, eyeball the code. That's pretty much it. And if you know of like multiple approaches, like let's say like you know how to traverse this tree in one traversal, also specify that, and then say like I would want to code it this way, approach 1 or approach 2, because I think approach 1 is simpler to code, or approach 1 has better time complexity, approach 1 has better space complexity, or something. So come up with a trade-off of why you want to do one approach or the other, if you know of multiple approaches.
Great. Thank you so much, Rocket Samurai.
Yeah. Okay. So yeah, if you have, unless you have any questions for me, I will sign off.
Yeah, no, that's awesome. Really appreciate the help, and hope you have a great rest of your day.
Oh, you too. Yeah. All the best. Bye bye.